Okay, so consider a link shared by n different sources, and these sources have their packet arrival rates, A1 up to A sub n. And let's model this as a discrete time queuing system with a single server and an infinite buffer space. Okay, now, what does the server represent here? The server represents, in our communication system queuing models, the server represents the link. The service time spent in the server is essentially the time spent in being transmitted through this link. The service time is related then to the transmission rate, inversely proportional to the transmission rate. The transmission rate in this case is C packets per time slot. For simplicity, let's consider equal-sized packets. Okay, so if the server can serve C packets per time slot, then the service duration of each packet is going to take 1 over C time slots. Okay. Suppose A sub I of t is the number of packets injected by source I in time slot t. So we have a discrete time arrival process model. So let's see. Assume the AIs of t's are IID across time and sources, with the expected value of the number of packets injected by link I, by flow I at time t, being below C over n. Okay, so then in terms of expectation, the flows are not overflowing the system. The expected rate over all the flows is below C. You will later see that this is necessary for stability. Okay. The sum arrival rate, in other words, is within capacity. Okay. Let Q of t be the number of buffered packets, in other words, the queue length at the beginning of time slot t. And we will assume that packets arrive at the beginning of each time slot and depart at the end of each time slot. So we will be able to write a certain queue dynamics equation as the following. The queue at the beginning of time slot t plus 1 is computed from the value of the queue size at the beginning of time slot t by adding any arrivals into the queue and subtracting the service capacity. If the queue was full, the number of packets served would exactly be equal to C. If the queue was not completely full and there are fewer than C packets, this would go negative. In that case, of course, it means that actually fewer than C packets have been served and the queue is empty at the end of time slot t. So in order to summarize that, we use this positive part. Basically, this is equal to, if the inside of the parenthesis is less than 0, set it to 0. So take the maximum of 0 and Q of t plus A of t minus C. Right. And it's down here. The positive part of a quantity is the maximum of the quantity and 0. Now, assuming the system starts at t equals 0 with m, let's compute this Q evolution by going 2 steps rather than 1. So let's first go 1 step. Q of k is Q of k minus 1 plus A of k minus 1 minus C, positive part. Okay, and then go 1 more time step. Q of k is now the maximum of 0 and Q of basically Q of k minus 1 plus A of k minus 1 minus C, which is the maximum of 0 and the maximum of this thing. But we can then simplify this to get this expression. And if you recursively apply this procedure from all the way down to time 0, you find that Q of t is maximum of 0 and the maximum of overall times k from 1 to t of A of t minus s minus kc. I would strongly recommend that you read and think about this expression. I think it's quite beautiful mathematically, because it says if at some point the maximum hits 0, it essentially restarts building up from that time. So wherever this expression, for whichever k this expression is maximized, I take that k. That is the total amount of service, essentially. So, I mean, think about this expression. So then the probability that the Q size exceeds a certain buffer capacity B, suppose, I mean, every practical computing system in real life is going to have a finite buffer capacity. And suppose that capacity is B, what is the probability that it is exceeded? That is going to be the buffer overflow probability, right? It is the probability that at some point k in time, this sum exceeds B. Okay. Now, I think I was wrong when I said the Chernoff bound is the only bound that we're going to use today, because I forgot that we're also using the union bound, which is a quite simple bound, but surprisingly effective at certain times. What is the union bound? Essentially, it says that the probability of A union B is less than or equal to the probability of A plus probability of B, right? So we are neglecting the subtraction of the probability of the intersection. And this may or may not be a good bound. For example, if the two events have no intersection, it's going to be met with equality, of course. But in general, it may be loose. So apply the union bound, meaning replace the probability of the sum by sum of the probabilities. And we obtain that the probability is upper bounded by summation k from 1 to t of the probabilities that the buffer constraint is violated at any time k. So basically, let's consider the meaning of what this is saying to us. This is the probability that the buffer is overflowed. This is the probability of buffer overflow at time k. And this is the general probability of buffer overflow. Buffer overflows at time 1 or time 2 or time 3 or time up to time t. So the buffer is going to overflow at some point from 0 to t, only if it overflowed at least one time instant time slots from 0 to t. So this is the probability of a union, but we are upper bounding with the sum of probabilities of overflow at time 1, overflow at time 2, overflow at time t. Okay. But then each of these things can be rewritten by raising e to the power essentially the left-hand side of the inequality and the right-hand side of the inequality. This is a very common trick, by the way, in probabilistic arguments like this. And then what do? Use Markov inequality again. And notice that the expectation of e to the theta times summation can be converted into a product of expectations, but each of these things are moment generating functions. I mean, it's incredible how we are making very rough approximate, like using union bound, which is in general very loose, and using Markov inequality, which is in general very loose. But then this is all going to get us somewhere interesting. Okay, so m of theta is the moment generating function of ai of t. What is ai of t? Remember? ai of t is a binary random variable. It's 1 or 0. Corresponds to the indicator of whether there's an arrival to flow I at time t. Okay, now let's define this lambda function, lambda of theta, to be the logarithm of the moment generating function of AI. Okay, then we can express this bound that we found in terms of that lambda function. You may say that this doesn't look like anything to me, but here is the significance. It's coming in the next slide. First of all, one easy thing to note from here is that the probability of Q overflow decays exponentially as the buffer capacity B increases, which makes sense. But next, is we're going to attach a meaning to this function delta of theta over theta, and it is going to be called the effective bandwidth of a source. So let's first see this, that the derivation we have done as a theorem. Our theorem says for all theta, such that, the logarithm of the moment generating function divided by theta is less than c over n, the Q overflow probability satisfies this. How do we get that? By manipulating the bound that we've derived. So this is the bound that we've derived, and we can express it like this. And when it turns out that theta, lambda of theta over theta is less than c over n, then e to the power n delta of theta minus theta c is less than 1, which implies that this is true. Okay, so the theorem holds. What is the theorem telling us? The theorem is telling us a bound on the buffer overflow probability in terms of this lambda of theta. Now, let's see the interpretation. Suppose AI of t takes values in a finite set, A1, A2, etc., AM. And it is not necessarily binary. Okay. So AI of t is the number of arrivals into flow, into the queue belonging to flow I that arrive at the beginning of slot t. Okay. And this takes values like 1, 2, 3, or, you know, arbitrary, essentially set of real values, A1 up to AM, ordered in an increasing fashion in this case. Suppose P sub j is the probability that AI of t is equal to A sub j. Okay. Now, suppose theta is close to 0. Then gamma of lambda of theta over theta is approximately equal to this expression, which goes to lambda as theta goes to 0. Okay. I mean, this follows from Taylor's series expansion, and this follows, the lambda follows by taking theta to 0. So what does that tell us? What does that tell us? The effective bandwidth of the source is approximately lambda. So what is lambda? If you remember, lambda is the total rate belonging to all of the flows. So let's go back to the definition. Let's see if we have it here. I believe I forgot to include a definition of lambda here. One moment. Let me take a look at my notes, written notes. Right. So lambda I, what we have is lambda sub I is less than C over N for all I. Okay, so C over N is the share of the capacity to each flow. Okay, now C over N is bigger than lambda over theta, and this varies between lambda to AM. What does this mean? So since lambda I is equal to lambda j for all I j, for all flows, we refer to as lambda, refer to all of it as lambda. So lambda is the average rate per flow. Okay, AM is the maximum rate per flow. Right. So as theta, the parameter theta goes close to zero, the effective bandwidth of the flows in total is equal to the mean. But as theta goes close to 1, if theta is very large, I'm not very close to 1, when theta gets very large, then this thing that is a bound for C over N, remember, goes to AM, meaning the sources act more like their maximum rates rather than their average rates. Okay, so the effective bandwidth of a source increases from the mean arrival rate of the source to the max arrival rate of the source as the quality of service parameter theta becomes more and more stringent. Okay, and the effective bandwidth is an increasing function of the burstiness of a source. This is very interesting. So I assign you exercise 3.5 as homework for next week. Actually, I recommend you do it by Wednesday. Burstiness of a source, what does that mean? Any comments? What is the burstiness of a source? And burstiness is the randomness of a source. For example, if a source is steady, it may be, if it is completely sending at rates, a fixed rate lambda per time unit, lambda per time slot, it is not bursty. Or a source could be active, only like 1% of the time, sending a large rate, and then idle. Like, for example, it's idle 99% of the time, such that it is active 1% of the time. And when it is active, it sends at the rate R. So R times 0.01 will give you lambda. The average rate is still lambda, but the source is bursty. It's when it is active, it sends a large rate R. So I mean, compare, for example, these two sources. One source is sending at rate lambda all the time. The other is sending at rate 2 lambda half the time. A very simple comparison. Okay. So